Welcome to this explainer. Today we're diving into Lecture 33 by Skip Uni, which is honestly a fantastic C++ array tutorial. If you've ever dealt with an array in C++, or if you've been banging your head against the wall trying to master arrays in C++ programming, you know they can be kind of tricky at first. But don't worry, because today our goal is to give you literal X-ray vision into your computer's memory. We're going to completely demystify pointer arithmetic. We'll be focusing heavily on how a one-dimensional array in C++ actually functions under the hood, starting right from a basic array declaration and initialization, all the way to some pretty advanced memory manipulation. So let's jump right in.
But first, I've got a quick question to challenge your assumptions. Can you actually add or subtract raw computer memory addresses? I mean, obviously we know we can add regular numbers together, but what happens when you try to do math with the physical locations inside your RAM? Does math even work the same way inside the machine as it does on a piece of paper? Well, stick around because the answer is absolutely going to change how you write code for sure.
Here's our roadmap for today. We'll start by visualizing arrays in memory, then cover the base address concept, adding to a pointer, pre- and post increments, and finally, pointer subtraction rules. Simple enough, right?
All right, Section 1, Visualizing Arrays in Memory.
Okay, so picture an array of 5 elements. We've got 10, 20, 30, 40, and 50. Now, in C++, arrays have a few unbreakable rules. First, they have a fixed size. Once you set it, that's it. Second, they strictly hold homogeneous data. That means all the data has to be exactly the same type, like integers in our case. No mixing and matching like you might do in Python. And crucially, arrays use contiguous memory allocation. Think of it like students sitting sequentially on benches in a classroom, right by their roll numbers. Oh, and remember, indexing always starts at 0. So if our computer decides to place that very first element, index 0, at memory address 1000, the rest just perfectly line up right behind it in a neat little row.
Moving on to Section 2, the base address concept.
So here's a really crucial takeaway. When you use the name of an array in C++, by default, it acts as a pointer to the very first element's memory address. So if our array is simply named R, typing R is literally the exact same thing as asking for the memory address of index 0. If we assign this array name to a pointer, let's just call it P, we're basically planting that pointer firmly at the starting line. In our visual model here, P is now anchored securely at address 1000.
But hang on a second. Think about those memory addresses we just mapped out, 1000, 1004, 1008. Why on earth are they jumping by 4? Well, it's because in this specific example, we're using integers, and an integer typically takes up exactly 4 bytes of memory. To figure out the total size of your array, you just do a quick calculation. Multiply the number of elements by the size of the data type. So our 5 elements times 4 bytes each means this entire array reserves exactly 20 contiguous bytes of memory. That number 4, that is the absolute secret key to all the math we're about to do.
All right, Section 3, adding to a pointer.
This brings up a really interesting rhetorical question. If p equals 1000 and we write p plus 1 in our code, does the address just become 1001? It's honestly the single most common pitfall when you're learning C++. You'd think so, right? It's just simple math. But remember, we aren't just doing grade school math here. We have X-ray vision into RAM now.
Here's the trick. Adding 1 to a pointer does not add one single byte. Instead, it jumps forward by the exact byte size of the data type. So when we write p plus 1, we're essentially telling the computer, hey, move forward by 1 full integer size. Since our integers are 4 bytes long, p plus 1 actually calculates to 1000 plus 4. The pointer just seamlessly jumps from address 1000 directly to 1004.
But wait, an address isn't the data itself, right? To actually grab the number 20 sitting at address 1004, we need a special operator. Dereferencing, which is represented by the asterisk symbol, is the act of going inside a specific memory address to retrieve or print the actual data stored there. It's kind of like having the address to a house. Dereferencing is using the key to open the door, walk inside, and see who's actually hanging out in there.
So if we put an asterisk outside the parentheses of p plus 1, we're successfully fetching the value 20 from address 10.4. But guys, here is a massive secret that trips up so many developers. Doing this specific mathematical operation is strictly temporary. Yes, it fetches the data, but the original pointer p itself, it remains anchored right back at address 1000. We basically just peeked ahead. We didn't permanently move our tracker.
Which leads us perfectly into Section 4. Pre- and post increments.
Now we have two very similar looking but entirely different operations. First up, the post increment, written as *p++. This grabs the data at the current address first, and only then does it permanently move the address forward. On the flip side, there's the pre-increment, written as *++p. Because the ++ comes first here, it takes priority. It moves the address forward first and then grabs the data at that brand new location.
Let's trace this mechanically, step by step. If our pointer p is currently sitting at the base address 1000 and we execute *p++, the computer first looks inside address 1000. It sees the value 10, and it prints it out. Only after it's totally done fetching that 10 does it permanently shift the pointer's base address to 1004. The pointer has officially taken one full step forward.
Now, assuming our pointer is resting at 1004, what happens if the very next line of code is *++p? Well, the pre-increment reverses the priority. Before it even bothers looking at the data, it moves the tracker. It jumps 4 bytes forward to address 1008. Now that it's all settled into its new home, it dereferences it, looks inside, and retrieves the value 30.
And just to round this out, subtraction works the exact same way, just in reverse. If we're sitting at 108 and run *-p, which is a pre-decrement, we immediately break our connection to 108, fall back exactly 4 bytes to 104, and then look inside to retrieve the value 20. You're essentially just sliding up and down that memory bench, fetching values instantly. And this speed and direct targeting is exactly why arrays give us the massive advantage of random access. You don't have to search sequentially, you just grab exactly what you need.
Finally, let's hit Section 5, Pointer Subtraction Rules.
Imagine we've got a pointer called start resting at address 1044, and another pointer called end resting at address 1016. If we execute end minus start, it doesn't just spit out the raw memory difference. In step 1, the compiler subtracts the raw addresses. 1016 minus 1044 gives us 12 bytes of distance. But then, in step 2, it automatically divides that raw distance by the byte size of our data type. So 12 divided by 4 bytes per integer equals 3. The output is 3. It brilliantly tells you exactly how many elements exist between those two pointers.
So to make sure you never get a syntax error again, we just need to burn a few golden rules into our brains. Number 1, you absolutely can subtract pointers to find the distance between them. Number 2, you cannot add two pointers together. It just makes no logical sense to add two separate memory addresses. The compiler is going to strictly reject it. And number 3, if you're doing arithmetic between pointers, both pointers must be of the exact same data type. An integer pointer and a character pointer just cannot interact because their stride lengths in memory are totally different.
We've covered a ton of ground today, completely mapping out how arrays live inside your computer's memory. So now that you possess this literal X-ray vision into RAM, how are you going to use pointer arithmetic to absolutely conquer your next technical interview? Just think about how incredibly efficient your code can be when you stop guessing and start directly commanding the memory. Thanks so much for joining me on this explainer. Keep practicing those arrays, and I'll see you next time.